Circuit analysis can be a difficult subject to grasp. In order to understand it a little bit better, let's see how we can relate roller coasters to circuits. Keep watching to find out how. In order to relate circuits to roller coasters, there are two things that we need to consider. The first is what's called Kirchhoffs Laws. These rules are a special case of what's called the continuity equation for charge and Faraday's law. The first of Kirchhoffs' laws is what's called the loop rule. It says around any closed loop, the sum of changes in electric potential are zero. The second of Kirchhoffs' laws is what's called the junction rule. This says that the sum of all currents going into some junction is equal to the sum of the currents leaving the junction. When applying Kirchhoffs' law, it's imperative to draw the directions of the current as well as the directions of the loop. By doing this, you'll be sure to have the correct signs for your loop equation. Let's look at Kirchhoffs' laws in action. The first example will be for two resistors in series. First, we must draw the direction of all currents. We notice that there are no junctions in this circuit, which means the current is the same through both resistors. Now let's draw the direction of our loop. Since we have our currents drawn and the direction of our loop, we're ready to write our loop equation. Let's start below our battery. As we move across the battery, this is going to be an increase in potential. So for our loop equation, we can write plus V. Then we hit our first resistor. This is going to constitute a decrease in potential. So we can write this as a minus V1. Then we get to our second resistor. Again, this is a decrease in potential. We'll write this one as minus V2. Now we get back to the beginning, and the sum of these potentials is equal to 0. For our resistors, we can replace the drop in potential with V is equal to IR. Now we have an equation that we can solve for the current. Now let's look at a simple example of resistors in parallel. In this case, we have a junction, which means we have to label all currents going into the junction and all of the currents leaving the junction. This says that I is equal to I1 plus I2. From this equation, we can see that there are three unknowns. This means that we'll need three equations in order to solve for the currents. To obtain the second two equations, we'll draw two loops that we'll label loop A and loop B. Going around loop A, we see an increase in potential from the battery, and then a decrease across the resistor R1. This means our equation for loop A is going to be V minus I1 R1. For our second loop, we see something similar. For this loop B, we see that V minus I2 R2 is equal to 0. Now we have a system of equations that we can solve for our currents. I promised earlier to talk about roller coasters, and we're almost there. The second piece we need to consider in order to treat circuits as roller coasters is what we talked about in last video. We saw that changes in electric potential could be treated as hills. This means when we draw our circuits and our loop equations, really what we're saying is that the sum of changes from hills is equal to 0. Now let's see what this means in our cutting-edge roller coaster simulator.
Here, I have a roller coaster representing our first circuit. The battery represents the lift hill. Each of the resistors is represented by the two hills that drop back to the beginning of the loading platform. We see a couple of interesting things here if we consider Kirchhoffs' rules. First, if we look at the current continuity equation, we see that if we equate the current to the number of roller coasters in a given line, the current should be constant. The roller coasters don't have a choice of where to go. They have to stay on the same track in this example. The second thing that we notice comes from the loop equation. We can draw a loop that goes around the direction the trains go. Here we see an increase in the potential for the lift hill and a decrease in potential for the two subsequent hills. The sum of this change in potential has to be 0. This is equivalent to saying the track is of continuous height. For any point on the track, if I go around in a complete loop, I will always return to the same height. We can see this by looking at the plot of the height of the roller coaster. It always smoothly changes. Now let's look at our parallel case for our roller coasters. This is equivalent to two roller coasters running right next to each other at the beginning. At some point, they split, so they go down separate hills. Let's see what the junction rule says about this. When the two roller coasters go up the hill, they are next to each other. This is equivalent to having two trains in one line. Then they split. Each of these lines has one roller coaster in it. The sum of the number of roller coasters going into the split is equal to the sum going out. This is a way that we can visualize the junction rule. Let's see what our loop rule says. For each one of the roller coaster tracks, we can draw a loop. For each of these loops, the train has an increase in potential from the lift hill, and then a decrease due to the drop in that line. Just as with our previous example, the change in potential around these loops has to be 0.
I hope our roller coaster example helps you better conceptualize what happens with circuits. That's it for this video. Thanks for watching.